So now we'll look at the definition or the idea of what is stress. So stress in particular can be described as a force exerted on an object per unit area of the surface where the force is being exerted on. So for example, imagine the weight of a steel drum sitting on a wooden support frame with four legs. So we've sort of looked at this idea before. The force is distributed to each of its four legs. The force being experienced by each leg is only being experienced on the area on the top of each leg. So let's sort of visualize what's happening here again. So we have a steel drum, and it's sitting on a wooden support. So just gonna sketch out. Obviously, it might not be the exact picture. And that wooden support has four legs. So say we have a leg here, we have a leg here, kind of a mini little table, and then obviously one under here. So it's being supported by those four legs. So we have this steel drum. Remember, it has a weight according to gravity that's being pulled down, associated with its mass. And that force is being distributed over all four. So we have also the force coming up in each of those values, and the weight or the full force is being only on the surface area of each of the legs. That's what's actually supporting it. So stress would be that same idea. So we haven't actually looked at the surface area component of it before. So the steel drum being forced down, we know the force up is equivalent to it, so we take that force and divide it by 4. But now when we're looking at stress, we deal with, okay, where is it on that particular support? So it's actually per surface area. So depending on what shape the legs are, in this case I've kind of drawn them as little cylinders, but the area would be where all of the weight is being supported or maintained, or where the stress is coming into play. So just like forces, we looked at different types of forces. There are different types of stresses as well. And the three we're going to sort of take a look at are sort of visualized down here in this diagram. So we have what's called the plane of expected breakage, so where things might snap under pressure or buckle under pressure. So we have a couple different types of stress we're going to look at. So tensile strength, remember tensile or tension we've looked at before, is the pulling. So that would be the pull direction. We denote that with a little sigma with a subscript T. We have a compressive strength. So again, compression, the idea of actually pushing towards each other. And again, we have that stress happening there. So this is denoted with little sigma subscript C. And then we also have shear stress. And that's when it goes in opposite directions. So it's not push or pull, but we're having that sort of shearing sort of left and right. And we denote that with the symbol tau. So the formula for stress is given basically by its definition. So it's the amount of force per area. So stress in the general situation, we're going to use the symbol sigma, and it's equivalent to force divided by area. And you can break that down into the different values if you want to. So tensile stress, sigma with a little t, F over A. Compressive strength or compressive stress, sigma C, F over A. And then your shear strength as well, F over A. So F is the force in newtons, and we've done the calculations of that before. A is the cross-sectional area in meters squared. So again, we're going to have to go back to our area formulas and look at those along the plane of expected breakage. So again, if you do want to find stress, you have to make sure that you're calculating force first and then plugging into that formula. As usual, you can go to your resource sheet. We have our area formulas, obviously related to area we've looked at before, and at the very end of your resource sheet, you do have the stress formulas as well in their different forms.